In this video, I'm going to talk to you about carrying out a factorial ANOVA using SPSS. Um, Basically, a factorial ANOVA is carried out in those cases where you have two or more categorical independent variables and a single dependent variable, typically considered continuous. So one of the nice things about factorial models is that you can look at the effect of each of your categorical independent variables separately, as well as consider any possible interactive effects. In other words, you can address the question of whether the relationship between one of the categorical independent variables and the dependent variable varies across levels of the other. So in this illustration right here, I'm going to show you how to carry out a two-way factorial ANOVA. And when I say two-way, I'm referring to the fact that we have two independent variables. A three-way factorial ANOVA would involve obviously three independent variables. Typically researchers don't get too far into three or four-way or any kind of higher level factorial designs, just because they become quite unwieldy. So oftentimes you'll see the researchers kind of utilize two-way designs for the most part. So in this particular illustration right here, I have data on 109 cases. We have individuals who received one of three interventions aimed to impact their perceived utility when it comes to statistics. So basically trying to kind of shape their perceptions of the utility of statistics for their futures. So the first variable is intervention, and it's basically coded as 1, 2, or 3. And then we have gender, and males are coded 1 and females are coded 2. And then perceived utility is our continuous dependent variable. So case 1 is a person who received intervention 1 who is a male, and this is that person's score on perceived utility. Case 21, that person received intervention 2, was a male, and this is that person's perceived utility score. So to run the ANOVA, what we do is we go to in SPSS is we go to analyze general linear model to univariate, and we place our independent variables, which are categorical, into the fixed factors box, and we put our dependent variable into the dependent box. Under options, we can select. Generally, I select basically the entire set of variables, which I seem to be having a little bit of problem here, but highlight them and move them over to the display means box, and then click on descriptives, effect size, power, and homogeneity test to address the homogeneity of variances assumption. Then click on continue. Under plots, I can ask for profile plots for the effect of intervention, gender, and also the intervention by gender interaction. So I'll move intervention over to the horizontal axis, click add, gender, do the same, and then to get the interaction, I'll move intervention over, and for this case I'm just assuming that gender has a moderating effect on the effect of intervention on utility scores, and then I'll click on add and then continue. I could also request post hoc tests if I want. If I click under post hocs, I can move intervention over to post hoc test. This only makes sense if your independent variable happens to have more than 2 levels. So gender would not make any sense to move over to try to do post hoc tests since it only has 2 levels. So in this case, I'll click on 2 keys and then continue, and then OK. So now in this particular output, you can see that we have a box of descriptive statistics. You can see that we have intervention A, B, and C. We have gender for each for the groups as well. So you can see that males who received intervention A, their mean utility score was 17. For females receiving intervention A, it was 17. Males receiving intervention B, scored on 19 on average, females scored 13 on average, and then for intervention C, males scored 19 on average and females scored 21. So basically what you can see right here, you have basically 1, 2, 3, 4, 5, 6 means that are being compared. So basically you have 6 cell means, and when I'm talking about cells, it's basically calculated, or the number of cells is just basically calculated as the number of levels for the first independent variable times the number of levels for the second. So we had 3 levels for intervention A, and we had 2 levels for intervention gender, which is our second independent variable. So that gives us 6 cells. So we have 6 cell means that would be compared when we're studying the interaction effect. When we're studying the main effect of intervention, we're just basically comparing those individuals in A, the cell mean across gender, against those individuals in intervention B across gender, and against those in C across gender. And then when we're looking at the main effect of gender, we're just looking at males versus females irrespective of the intervention. So this is males on average, their perceived utility score on average, as compared to females' average perceived utility score. So now those are just some basic descriptives, and so now we can start looking at test results, whether there are significant effects of the independent variables and the interaction effect. First, I want to highlight up here you get Levene's test of error variances. This is addressing the question of whether there are homogeneous variances. So I'm just going to call it HOV, homogeneity of variances with respect to perceived utility across those cells. So if I kind of scroll back up here, you can see we've got the standard deviations for perceived utility within each of the cells. And so what we're looking for are relatively similar amounts of variation across cells. And so we don't want to see substantially different amounts of variability in utility scores across those cells. If we do, then that's going to suggest that we have heterogeneity of variances, which is a violation of a key assumption related to analysis of variance. So to address the homogeneity of variances assumption using Levene's test, we can see it's basically an F-test, and you have right here printed out is a p-value. So the p-value is equal to 0.999 for this particular data set. And conventionally, when you're running standard significance tests, testing out various hypotheses, you actually are looking for p-values that would be less than 0.05 or less than or equal to 0.05. And that's actually what tends to be considered a good thing. In the context of testing your assumptions like homogeneity of variances, this is actually a bad thing, because this would mean that we are violating our assumption. So here we see that the p-value that is printed out is actually greater than 0.05, and basically that is a good thing. So that would suggest then that our assumption of homogeneity of variances has been met. And that allows us to feel more trustworthy when it comes to assessing our effects in our ANOVA summary table. So moving down, you can see that we have now 3 effects. We have intervention, gender, and then we also have the intervention by gender interaction effect. So you can see for each of these effects you have sums of squares associated with them. You also have degrees of freedom associated with each of those effects. So basically, what we're trying to do is to determine which, if any of these, or all of them for that matter, are statistically significant. So we essentially are looking at the F-test for each of these effects. So you can see right here the mean square. This is just basically calculated as a ratio of the sum of squares for the effect, in this case intervention, divided by degrees of freedom for the intervention effect, and so that's the mean square right there. The degrees of freedom for the effect for intervention is just the number of groups minus 1. For gender, you also have the sum of squares divided by degrees of freedom, which again is just taking the sum of squares divided by the number of categories minus 1, which obviously leaves us with 1, and there's our mean square as well. And then you also have your sums of squares for the interaction effect and degrees of freedom, and that gets us when we take that ratio, we get the mean square for the interaction. Finally, you have the mean square due to error, which is right here, which is formed by just taking the error sum of squares, dividing it by the degrees of freedom, and there you go. So the effect for intervention, the F value that you see right here, is just basically taking the mean square for intervention and dividing it by the mean square error, and so there's your F value. For the F value for gender, it's just mean square for gender divided by mean square error. And then for the F value for the interaction effect, it's just mean square for the interaction divided by mean square error. So these are all the F values that you see printed out here. In this column right here, these are P values, and SPSS rounds off to 0.000. So in all basically there's no zero P value, but that's just the way it's printed out. So typically researchers will report a P value that looks like this. They'll report it as P is less than 0.001, because the actual value could be 0.000001 or something like that. So at any rate, let's say we assume an alpha level at 0.05, then you would see that really all three effects are statistically significant. There's a significant main effect for intervention, a significant main effect for gender, and a significant interaction effect when it comes to intervention by gender. In this column right here, these are effect size indices. So this allows you to, it helps you to gauge the magnitude of the effect for our effects in the model. So conventionally, for the social and behavioral sciences, Cohen laid out the following general thresholds or conventions for what's constituted as a small, medium, or large effect. So 0.01 value would be considered small, 0.06, around 0.06 would be considered a medium effect, around 0.14 or larger would typically be considered a large effect. So you can see right here, looking at these three values, you have a large effect using Cohen standards for intervention, probably a medium or moderate effect for the gender effect, and then also a large effect for the interaction. So basically, at this point, it looks like that all three effects were statistically significant. All three effects were significant in the model, and we had fairly large effects overall. Except, gender was more modest, but still, there was one present. So now, following, you can see estimated marginal means. So you get the grand mean, as well, you basically get the grand mean down here for utility, as well as the group means for males and females and intervention. These all appear in the descriptives above, but you also get standard errors, the confidence intervals, and so forth. You also have the means and standard errors for each of the interaction or the cell effects, if you will. So when we scroll down and we can look at the post hoc test, you can see right here, you can see that we had two key post hoc tests. We were comparing the intervention. So you got I and J columns right here. So what's printed out in these columns, in this column right here, are just the mean differences. So if you take the mean for intervention A, subtract the mean for intervention B, you get 0.727. So meaning that really intervention A, folks in that intervention scored about 0.727 points higher on average than those in intervention B. Over here you get p values, and these are basically non-directional tests. So you're just comparing against alpha level that you set again, conventionally it's 0.05. So you could say right here that there's no significant difference between in utility scores between those in intervention A and intervention B. When we look at intervention A versus C, you can see that we get a negative value. Mean, obviously if you take the mean for A, subtract the mean for intervention C, if you end up with a negative value, then that means that those folks in intervention C would have had to have scored higher than those in intervention A. In fact, they scored about 3.297 points higher on average than those folks in intervention A. The difference between groups was statistically significant. Now, when you look at intervention B versus A, this is just a rehash of what we had right up here in this first row. So there's no need to actually bother with this particular finding. So now we'll just go to intervention B versus intervention C. And you can see that we have a negative value, meaning again that those folks in intervention C would have had to have scored higher than intervention B. And in fact, it was about 4 points higher on average than intervention B. The difference was statistically significant. Then when we look down here at intervention C versus A and C versus B, well, that's just a replay of what has occurred above. So there's really nothing else to look at in terms of this table. So the difference between A and C and B and C, those differences were all statistically significant. So looking at our profile plots, you can see this is just a plot of the intervention effect on perceived utility scores. You can see again, this is the, along the y-axis, these are the means. Along the x-axis are interventions. So C is higher than B in terms of the means, and C is higher than A. So that's, all that is basically replaying what we saw above in our little test of mean comparisons here, our post hoc test. When we look at gender, you can see that males scored higher on average than females, and that's just basically rehashing what we saw in terms in the ANOVA summary table. Then we get to some of the interesting things in terms of potential interaction effects. If there was a non-interactive effect, then basically both of these lines would be parallel. So it wouldn't matter what it would look like, if we had intervention, A, B, and C, which is terribly drawn here. But if you had something like this for let's say this is for males, and then we had this for females. If they're parallel, then that would suggest that we have a lack of interaction. Or by the same token, if you had something like this, in this case right here, what that would, what you would see is that, well, the lines are parallel. Even though they would be curvilinear in shape, you can see that the distances between males and females across those are equal, and the same would be right here, which would signify a lack of interaction. We don't have that situation here. You can see in this particular plot that there's no difference between males and females in intervention A. You see that there's a substantial difference between males and females in intervention B, where basically males scored higher on perceived utility than females. And then you actually had a crossover effect here, where you have a difference right here, but you can see now that females are scoring higher than males. So basically you can see that there's no parallel lines. But let's say, for instance, that let's say for males, let's say for argument's sake that the distance was down here, and so it mirrored the same distance that we see right here. In that case, because there's still a crossover, that would be an indication that we have an interaction that's taking place. So overall, it looks like that the relationship between intervention and perceived utility scores varies depending on whether you are a male or a female. You can further break down some of this information if you run simple effects contrasts or simple effects tests. The way that you can do this is to go back through the original menu, and if you'll click on paste, then some syntax will come up, a syntax file that gives you basically everything that you've already specified via the menu button options. So if you'll find in here, this is the table. This is asking for the table of means or cell means for intervention by gender. And so what I can do in this particular case is I can say, well, I want to compare, let's say I want to compare males and females in each gender group. What I can use is the compare command. So I'll say compare, and then I will type in gender, which is the name of my independent variable. And if I want to add in any kind of Bonferroni adjustment or something like that, I can just type in ADJ and then Bonferroni, and then in parenthesis. And so now if I highlight everything and run it, when I scroll down, you can see that now I get those simple effects tests. So as you can see right here, I have a test of males versus females in intervention A. And so you can see this I minus J, so there's the mean difference, which is 0. And so the p-value was 1. So it's obviously indicating that there's no difference between males and females in intervention A. When I look at intervention B, when I take I minus J, you can see that males would have scored higher than females because this value right here is positive. And there is a statistically significant difference between the two groups, with males scoring higher on average than females with respect to perceived utility. Then when I look at intervention C, males versus females, you can see that the sign is actually reversed and it's actually negative now, meaning that females would have had to have scored higher than males. And the p-value right here is 0.011, indicating that there is a significant difference between males and females in that particular intervention group. So basically, what we can see based on our analyses is that yes, there does appear to be a significant main effect of gender. Meaning that irrespective of the intervention condition, males and females differed on perceived utility. With respect to intervention, there were significant overall mean differences, irrespective of the gender of the participant. So there were significant intervention group differences on perceived utility. And then we also have a significant interaction effect. So in other words, the relationship or the mean differences that we observe on utility vary across levels of gender. In terms of writing this out and reporting this kind of in APA format, I can't really write it out too well with this little marker here, but I will say that it's oftentimes the case where researchers will say something to the effect that there were significant group differences or intervention group differences on the dependent variable. They'll specify F, and then they'll give the degrees of freedom between and degrees of freedom within. So for intervention, the degrees of freedom between are 2. Intervention degrees of freedom error or within is 103. Oops, 103. And then kind of an in parenthesis. And then they'll give the F value, which is 29.273, 29.273, and then P is less than 0.001. As I said, it's the way SPSS rounds us off, it looks like it's 0 when in fact it's not really. For the effect of gender, basically you would say there were significant gender differences. You could say degrees of freedom 1 is between, 103 is degrees of freedom error or within. And so that's in parenthesis, and then equals 9.346, 9.346, and then P is equal to 0.003. And then for the interaction effect, it would be reported using F, and then you can see you've got 2 degrees of freedom and 103 for error. So 2 for between group degree of freedom and 103 for the error. So you can see that the degrees of freedom error are the same, irrespective of which effect you're talking about. Then we would say 28.975. And once again, we'd be using P less than 0.001. So I will say that obviously it's a little hard to write with this little edit pen, but one way to kind of learn about how to write things up and develop some stylistic understanding is just to read research reports that report on different statistics like Factorial ANOVA, and see how those results are reported. So at any rate, that concludes this video on Factorial ANOVA, and I hope you found it helpful.